So the topic for today's lecture is thermodynamic equilibrium. So now let us try to understand that what is thermodynamic equilibrium and how to understand what is meant by thermodynamical equilibrium. We'll try to understand what is meant by thermodynamical equilibrium today. So firstly here, in order to understand this thermodynamic equilibrium, we should understand what is meant by equilibrium first. So let us see what is equilibrium here. Equilibrium. If I take classical mechanics into consideration, the definition of equilibrium will be completely different than we try to study what is meant by equilibrium in terms of a thermodynamics. So first let us understand what is meant by equilibrium with respect to classical mechanics. In the classical mechanics, equilibrium means whenever the net force and the torque applied on a system is zero. If the net force or the total net external force and the torque applied on the system is equal to zero, then we can say that that particular system is in equilibrium. So now if you talk about mechanics, in the mechanics, if the applied force, the external applied force and the torque, if both are equal to the zero, we say it as an they are in mechanical equilibrium. So now here, if net force and torque applied is equal to zero, then we call it as an that particular mechanics is in equilibrium. It is in equilibrium. But first let us understand what is meant by torque first. What is torque? Torque, if I need to take an example of torque is nothing else but it is a force which is applied on a system or on a body with a perpendicular direction. It's a force applied on a system with a perpendicular direction. So see now, if I am holding this marker and you can see this one, I can even remove this one, this particular nib of marker I can remove it. Means what I am actually doing, I am trying to apply the force over here. If I am applying the force, what is that force happening? The force is traveling perpendicular to this particular distance where actually that force has to be applied. Where the force has to be applied? The force has to be applied where this particular screws are located. If I need to apply a force, then that force will travel perpendicular to the area where it has to be applied or to the point where it has to be applied. Then the rotation of that particular point will take place. The rotation of this particular point will take place. So this is, I can say that the force which I applied here is a perpendicular directional force. So I can call it as a torque. Torque is nothing else but it is a force which is applied on any of the point with respect to perpendicular distance. If you apply a force at any of the point with respect to perpendicular distance and that force is causing the particular point to rotate, we call it as an torque. That is one example now. The another example, take an example of a door. If you take an example of a door, what happens? If you want to open the door or if you want to close the door, what you will be doing? You will be applying a force on the holder of a door. If you will be applying a force on the holder of the door. If you apply a force on the holder of the door, what happens? The force will travel perpendicular distance to the edge of the door where the hinge is located. Where the hinges are located. Hinges is nothing else but which connects the door with the wooden piece which is in the wall. So now that hinges, if you apply a force on the holder of a door, the force will travel perpendicular distance until the hinge and then that particular force will be indirectly applied on the hinge so that the hinge will be rotating. You can see that one, you can see the motion of the hinge. When you try to apply a force on the door, the hinge which is located between the wall and the door will be rotating. That rotatory motion is being caused by this force. So I can say that the torque is nothing else but it is an rotational aspect of the linear force. You will be applying a force in a linear direction, but that linear directional force will cause a rotatory motion at the point where the force has been applied. So that is called as an torque. So torque is nothing else but if I talk about torque is a rotational effort due to a linear force. Due to a linear force. So it is a rotational effect due to a linear force. So now this torque is being denoted by, it is denoted by tau. Tau, it is denoted by tau. So now it is a product of force applied and the direction of this particular force, and the direction, that's a perpendicular direction. So it's a force applied by the perpendicular direction of distance. It means that this r is nothing else but r is the perpendicular distance which the force will travel in order to make that rotatory motion at the point where you want that force to be applied. So now torque is a rotational aspect or rotational effort due to a linear force. So because of this reason, I can even call the torque has the other names of the torque is, you can call it as couple. You can call it as couple. It is also called as moment. It is also called as moment of force. Moment of force. It is also called as turning force. It is also called as rotational force, etc. So these are the different names of a torque. So these are the different names of a torque. Torque is nothing else but it's a rotational effort applied at a point due to the linear force. So the other names of torque is couple, moment, moment of force, turning force, rotational force. So this is regarding what is meant by torque and what is meant by equilibrium in classical mechanics. If you talk about the classical mechanics, the equilibrium means if the net force and the torque applied on the particular system is equal to 0. Whenever the net force and the torque applied on the particular system is equal to 0, we say that particular system is in equilibrium. But this will not be the same when we go into the topic of thermodynamical equilibrium. In the thermodynamical equilibrium, the concepts will be completely different. So now we are supposed to understand what is meant by thermodynamical equilibrium. Now we'll try to see what is meant by thermodynamical equilibrium. So now here we have understood that equilibrium means, if you talk with respect to your classical mechanics, the equilibrium, the concept of equilibrium or the concept of your particular system is going to be changed when you talk as an equilibrium. If you say it's an mechanical equilibrium, the total amount of net force applied on the system and also the torque which is applied on the system, both are equal to 0. But when we come to the thermodynamical equilibrium, the concepts are completely different here. Yeah, in the thermodynamical equilibrium, it means that whenever the thermodynamical variables, we know different kinds of thermodynamical variables. The thermodynamical variables are nothing else but like pressure, volume, temperature, number of moles, entropy, internal energy. All these are the different types of thermodynamical variables. Now here, if a system is said to be in thermodynamical equilibrium, it means that these variables, these thermodynamical variables will not be changing with time. It means the pressure, volume, temperature, internal energy, entropy, number of moles, all these thermodynamical variables will not be changing with time. Then only we can say that that particular system is in thermodynamical variables. So let me give one example. If I consider a gas which is filled in a rigid container, what is a rigid container? Let me take an example of a gas cylinder. The gas which is filled in the gas cylinder will be constant even if we don't use it for some n number of days. It means the pressure, the volume and temperature and different types of thermodynamical parameters, number of moles, everything will be constant. They are not going to change with respect to time. Even if you put the gas cylinder without using for n number of days, that is with respect to time, these variables, the pressure of the gas or the volume of the gas or the number of moles present in the gas will be constant. They are not going to change. If that is happening, we say that that particular gas cylinder or the gas which is filled in a rigid container is in thermodynamical equilibrium. In the thermodynamical equilibrium, what happens is that all the thermodynamical variables which specify or which define or which categorize the system will be completely in constant. They are not going to change with time. So that kind of systems we call it as an thermodynamical systems. In thermodynamical or dynamic system, the thermodynamical parameters or variables will not change with respect to time. Then this thermodynamical system is called is in equilibrium. Okay, see now, thermodynamic equilibrium means what? All the variables in the thermodynamic system will not be changing with respect to time. So for this one, let me give one example. Let me consider two systems which are in thermodynamical equilibrium. It means that let me take two systems separately. I will be considering two systems. Let system A and system B. Let me assume that the system A and system B is with some different kind of gas, filled with different kinds of gas. Now, what I do is that here, first in between the two systems, I'll try to put some adiabatic wall. I have taken the two systems, system A and system B. Then I have filled the system A and system B with different types of molecules and atoms of different gases. So now this is a system A with different gas and it is a system B with different gas. So what is happening here? Between the two systems I have kept one wall which is adiabatic in nature. What is meant by adiabatic? Yeah, good. In the adiabatic, what happens ma? In the adiabatic, there will be no transferring of heat energy. The heat energy will not be transferred from one system to another system. If the heat energy is not transferred from one system to another system, then the parameters in this one, the thermodynamical parameters in the system A and the thermodynamical parameters in the system B are not going to change. They are going to be constant. So that's what happens with the adiabatic wall. If you are taking the two systems, system A and system B, and if you have put an adiabatic wall, what is this adiabatic wall? It is a wall which acts as an insulator. If it is not allowing the heat to transfer, it means that it is an insulator. It is acting as an insulator, and it can also be the movable wall. So it acts as an insulator. If it is acting as an insulator, it cannot transfer the heat from A to B or from B to A. There will be no transferring of heat from A to B and B to A. If there is no transfer of heat from A to B and B to A, what happens? See, normally whenever any gas is subjected or any matter is subjected with respect to heat, we know that the particles of that one will get altered, or the molecules or the number of moles or the atoms are going to be altered. If this molecules or number of moles or atoms are being altered, we know that definitely what happens? The system configuration is going to be changed. So that's why if there is no transferring of heat, then definitely this system parameters or the thermodynamical variables will be constant. There will be no change between the system A and system B's thermodynamical variables. Now let me take another consideration where I'll be having the same systems A and B. here between the two systems, I'll be putting now here, I'll put dithermic wall. I'll put a dithermic wall. What is this dithermic wall? It is a conductive wall. It is a conductive wall means what does it mean, conductive wall? It will be allowing the transfer of heat. In this case, the heat will not be transferred. But here in this case, the heat will be transferred. Once the heat is transferred, what happens? Then definitely all the thermodynamical variables which are present in this system A and system B are going to change, So let me assume that the pressure of this system A is initially is equal to PA and the volume of system A is equal to VA initially. And in the same case, let the pressure of the system B is PB and volume equal to VB. So now, if these are the initial case pressure and volumes of two different systems, whenever a conductive wall comes into picture between the two systems, then definitely the heat transfer takes place between the two systems. If the heat transfer is happening, what happens? The molecules or the number of moles are going to be altered. It means that there will be change in the pressure, in the variables like pressure, there will be change in the volume. How does the volume changes? We know that the number of, the volume is directly proportional to n number of moles. What kind of law it is? We have studied this particular law. It is regarding what? We have studied in the gas laws, Avogadro's law. As per the Avogadro law, it states that the V is directly proportional to n number of moles. So once if the volume is changed, if the number of moles is changed, then definitely the volume also gets affected. So that happens with respect to this heat transfer. If the heat is transferred between the two systems, the variables or the parameters in the two systems are going to change. If these parameters are changing, then definitely the system configurations are going to change. Then now, my question is that until when this heat transfer will take place? Until when this heat transfer is going to take place? The heat transfer will take place until both the systems have the same configuration of parameters or variables. It will be having the same configuration. It means that it will be having the equal amount of mass or equal amount of pressure, equal amount of volume or equal amount of entropy or equal amount of number of moles on both the systems. Whenever it has got equal amount of pressure, volume or number of moles or different kinds of thermodynamical parameters, then we can say these two systems are in thermodynamic equilibrium, are in thermodynamic equilibrium. So now, initially we have considered that PA, VA and PB, VB are the initial pressure and initial volumes of two systems. Now, once the thermodynamic process has completed, then what happens? This will be the new pressures and new volumes of the two systems, P-B and B-B. What does this mean? Once the thermodynamics two systems come into thermodynamical equilibrium, it means that P-A equal to P-B and also V-A equal to V-B. Whenever these parameters or the variables are same on both the sides of the system, the transferring of heat takes place. If the heat transfer is stopped, if the heat transfer has stopped, then we can say these two systems are in thermodynamic equilibrium. So this is regarding what is meant by thermodynamical equilibrium. System has to be in thermodynamical equilibrium. Firstly, it should satisfy mechanical equilibrium. It should satisfy mechanical equilibrium. Second one, it should satisfy thermal equilibrium. Third one, it should satisfy chemical equilibrium. So up to now we have understood that what is meant by thermodynamic equilibrium, and now if this particular thermodynamic equilibrium has to be in that, it means that if the two systems has to be in thermodynamic equilibrium, that particular system should satisfy this one. What is this? Mechanical equilibrium, thermal equilibrium and chemical equilibrium. If these three equilibriums are satisfied, then only I can say that the system is in thermodynamical equilibrium. So now, what is meant by mechanical equilibrium? If I talk about with respect to the classical mechanics, the mechanical equilibrium means no mechanical work is done. No mechanical work is done. But when I come to this thermodynamical equilibrium, the mechanical equilibrium means the system and the surrounding area, will be having balanced forces. The forces which is acting on the system and also the surrounding area will be balanced. It will not have unbalanced forces between a system and the surrounding area. Whenever you have got a balanced amount of force, what amount of force is applied on the system has to be the same as the force applied on the surrounding area. Or else, if I am talking about the mechanical equilibrium between the two bodies, then here what amount of force applied on the one body should be same as the force applied on the another body. Whenever both the systems are having, or a system and a surrounding area is having the balanced forces, we call it as an mechanical, the particular two systems are in mechanical equilibrium. Then coming to the point about thermal equilibrium. Thermal equilibrium means what? If a system has to be in thermodynamical equilibrium, it has to satisfy the thermal equilibrium. Thermal equilibrium means there is a sharing of temperatures between the two systems. Then the sharing of temperatures or the transfer of temperature from one system to another system will stop only when both the systems are with equal amount of temperature. It means that whatever the temperature is been released by one system has to be absorbed by the another system, and this releasing of temperature and absorbing of temperature between a system and surrounding takes place. That is what we call it as a transfer of temperature. The transferring of this temperature between a system and surrounding takes place until both the systems or both the environments, both the surrounding area and the thermodynamic systems have got the equal amount of temperature. If it is having equal amount of temperature, then only we can say that two environments or the system and the surrounding is in thermal equilibrium. If it is a thermal equilibrium, the system, thermodynamic system and the environment will be having the equal amount of temperature. So that has to be satisfied. The next one, coming to the chemical equilibrium. Chemical equilibrium, it is completely regarding the chemical properties of particular matter which is present in the system. It means that the chemical compositions, the number of moles or whatever it may be, it's regarding the chemical composition. The chemical composition of a system and the surrounding area both should be same. If both are same, then we can say that system and the surrounding area is in chemical equilibrium. Once these three equilibriums are satisfied, we say that system and a surrounding area is in thermal equilibrium, or else we can say both the systems are in thermodynamical equilibrium. So that is regarding what is meant by thermodynamical equilibrium. Let us see now what is meant by Zeroth law of thermodynamics. Statement. It states that two systems are in thermal equilibrium with third system separately then that two systems are also in thermal equilibrium. The statement of thermodynamics Zeroth law, it goes out like this. It states that two systems are in thermal equilibrium with the third system separately, then that two systems are also in thermal equilibrium. So let me consider that the first two systems are A and B, system A and system B, and the third system is system C. So I'll try to explain this concept of zeroth law with the help of a diagram now. So see now, let me consider this is my system A with some matter. This is my system B with some composition of matter, and now these two systems are now connected with adiabatic wall. In between the two systems there is an adiabatic wall. It is an adiabatic wall is nothing else but it's an insulating wall which will not allow the transferring of heat energy. It will not allow the transferring of heat energy. So it is now connected with an adiabatic wall between the two systems. Now let me have another system, system C, which is again composed of some matter, and this system C is connected to two systems by conducting wall, by a conducting wall, which we can even call it as an diathermal wall. It's a diathermal wall. So see now, if I am having the two systems, system A, system B, which is composed with some matter, and now these two systems are not in thermal equilibrium. These are not in thermal equilibrium. Now if I try to put these two systems in thermal equilibrium with system C, what does the statement states? It states that the two systems are in thermal equilibrium with the third systems. It is in thermal equilibrium with the third system separately. It means that since here the system C is connected to system A through a conducting wall, then definitely what happens? There will be a transferring of heat takes place between system A and system C. And in the similar case, system C is connected to system B through a conducting wall. So that's why the transferring of heat takes place between system C and system B. So now what happens here? Whenever the transferring takes place, the parameters of the thermodynamic systems will be changed or will be altered, and that alteration of the parameters takes place until the transferring of heat takes place. Once the parameters on both the systems are same, then the transferring of heat will stop. If the transferring of heat is stopped, or the flow of heat energy from one system to another system is stopped, we can say both the systems are in thermodynamical equilibrium. What does it mean? If the systems are in thermodynamic equilibrium, it means that it is having the same parameters or same thermodynamic variables. So now system B and system C are in thermodynamic equilibrium. It means that the parameters of system C is similar to the parameters of system B. So I can say the system C is in thermodynamic equilibrium with system B. Now here also, the two systems are in thermodynamic equilibrium with the third system. What are the two systems? System B, system A. Now these two systems are separately is in thermodynamic equilibrium with the third system separately. Means what? These two systems are separated by some insulating wall. It is an insulator, so you cannot expect any kind of heat transfer between A and B. There is a conducting wall between system B and C, and also between system C and A. So the heat transfer only takes place between C and B and also C and A. So because of this heat transfer, these two systems, system C and B and system C and A, will come into thermodynamic equilibrium. Whenever these two systems are in thermodynamic equilibrium, then automatically these two systems are also in thermodynamic equilibrium. Let me give one example how these two systems which are separated by an insulating wall or adiabatic wall are in thermodynamic equilibrium with respect to temperature. I'll take an example of temperature. I'll show that three systems are in thermodynamic equilibrium with respect to temperature. So see now, once these two systems, system B and system C, comes into thermodynamic equilibrium, I know that the thermodynamic equilibrium is satisfied when the system is having the mechanical equilibrium, or the system is in thermal equilibrium, or the system is in chemical equilibrium. So I'll take an example of one that is thermal equilibrium. So now if the two systems C and B are in thermodynamical equilibrium, it means that these two systems will be having the same temperature. It will be having the equal temperature. Let the temperature is equal to TB, temperature of B, system B is equal to temperature of system C. Temperature of system B is equal to temperature of system B. Now, where these two systems, system A and system C, are also in thermodynamic equilibrium. Now here, I'll take this example with respect to thermal, that's with respect to temperature. Then here also, temperature of system C will be same as temperature of system A. Then what happens here? Temperature of system C is same as temperature of system A. So see now, if temperature of system B is equal to temperature of system C, then temperature of system C is equal to temperature of system A. We can say that automatically the temperature of system A is equal to temperature of system B. So I can say that the thermal equilibrium, the system B and system C are in thermal equilibrium, and also system A and system C are in thermal equilibrium. So then I can say that all these temperatures are same. Automatically I can say that the system A and system B will also be in thermal equilibrium. So anyway, one of the situation is satisfied. So automatically what happens? Completely all these three systems will be in thermal equilibrium, and then it will be in thermodynamical equilibrium once they are in even though if they are connected through this conducting or insulating, through this adiabatic wall. So now if any of the two systems are in thermal equilibrium separately, then this third system also will be in this one. Then these two systems also will be in thermal equilibrium. So this is a concept about what is meant by zeroth law of thermodynamics. In the zeroth law of thermodynamics, there will be three systems. Two systems will not be in thermal equilibrium, but the two systems will be in thermal equilibrium separately with the third system. So then if these two systems are not in thermal equilibrium, they will be separately in thermal equilibrium with the third system, so that automatically all the three will come into thermal equilibrium in this way, in this fashion. So that is the statement of your zeroth law of thermodynamics. Now let me replace this wall. With an I'll replace the adiabatic wall with a conducting wall. Let me see what happens if I replace the adiabatic wall with a conducting wall. Now assume that this wall has changed to conducting wall. It has now made as a conducting wall. What happens here? If I change the wall, there will be no transferring of heat energy. The heat energy transferring will not take place, even though a conducting wall is placed between the two systems where the adiabatic wall was there previous to that one. So now what happens? Why does the transfer of heat doesn't take place? Because already the systems are in equilibrium. Already the system is in equilibrium. There will be no difference in the thermodynamical parameters. So that's how the transferring of heat will not take place. So this is even applicable for the thermodynamic equilibrium also. Even in the thermodynamic equilibrium, if you change the adiabatic wall with the conducting wall, the transferring of heat will not take place. So this is a concept about what is meant by zeroth law of thermodynamics.